All right. Okay, so we'll go ahead and get started. We were able to get through, I don't know. I think I'm just guessing when I throw those blank slides in. So we were able to get through a decent amount, all the way through here, I think, in my other class. And usually that one's, if anything, slower. So we'll aim to get through that today as well. Okay. So looked like the homework, hopefully it went okay for you guys. It looks like a good amount of people were able to get it to 100%. It's obviously the goal. So you'll have another one of those for chapter 2 due on next Sunday night. So just try to start working on that now. You're going to have, I don't know, probably half of the topics done by today, maybe a little bit less than half. But you can definitely make a good start on it. Okay? I've got the roll on like a clipboard, and I think it actually has everyone's names on it. So ours starts on the second page, just says 10 a.m. down there at the bottom. It's 2 pages, so just flip up as needed. I'll go ahead and send that around. What else? I guess that's it for now. Okay, so we finished last class talking about the components that make up an atom. And we primarily focused on protons and electrons, remembering that protons is really what's defining the properties of an element. And so when we talk about a particular kind of element, we're talking about the number of protons, okay? So if we say, I think the example in a second is neon. Yeah, so if we say 10 protons, we're talking about neon and it has particular properties because it has 10 protons. Once we start talking about 9 or 11 protons, all bets are off. The properties are not going to really align with that. In fact, as we'll see pretty soon, there are things that align much more readily with neon that are much further away in their number of protons. So the number of protons, just because it's close, doesn't necessarily have an indicator on how close its properties are. But every element is defined by that number of protons. Okay? All right, then we talked about electrons as well, which if nobody says otherwise, you can assume that the atom has not reacted or lost any electrons or gained any. And so we would say that it's neutral, meaning that it had the same number of electrons as protons. So for that neon example that we're going to do, we would expect neon to have 10 electrons as well, unless we were told otherwise. Okay? These examples here, sodium plus and fluorine minus. Those are if something lost an electron, we would consider it a positive charge because now it has one less electron than protons. If it has a negative charge, F minus, that would be if it gains an electron. So now it has one additional electron more than protons. So the one we didn't really talk about yet is neutrons. And when those vary, it does not change the element or the charge. It only changes the mass. Okay? So you can have neon. So let's scroll down here so we've got our neon example ready to go. So you can have neon that has 10 protons and 10 neutrons. You can also have neon that has 10 protons and 11 neutrons, or 10 protons and 12 neutrons, okay? It's still neon. You're just changing a neutral particle in there. When we change the number of neutrons, that's called an isotope. All right, so in a second, we'll talk about isotopes on the next slide and kind of why they're important and how we indicate them. I guess I'll talk about it a little bit here. So we're going to talk about symbols, how we represent different atoms in different ways. You know, one of the most ones that you're going to be familiar with is what it looks like on the periodic table, and that's the one on the bottom, an example of just like in a box with the symbol. Usually you're not going to have the name there. I'm not sure why we show that. Like, I don't think any periodic table really gives the name and the symbol. It's kind of redundant. Okay, so it has the atomic number, which is equal to the number of protons, okay? So atomic number here equals number, I'm going to write that and then it's going to be up there, isn't it? Yep, right there. Atomic number, number of protons. Apparently I just need to highlight things instead of rewriting them. The other key information that's going to be on there is the mass. So it's listed down here at the bottom, and it's in units of atomic mass units, so AMU for short, per 1 atom. So 1 atom of neon has a mass of 20.180 atomic mass units. The reason why it's not in like grams or anything is because these are so teeny tiny, it's impossible for us to think about them in terms of grams. It would be like 10 to the negative 30th of a gram or something. It's ridiculously small. Okay, so we have it has its own unit measurement for measuring mass of atoms. That unit of measurement, though, if you remember, makes it so that protons and neutrons are pretty darn close to 1 atomic mass unit, and electrons are very small by comparison. So you don't need to understand why protons and neutrons are not exactly 1. That's just additional information you don't need to worry about. But knowing that they're close to 1 is useful, because not only will we sometimes use the mass number, the atomic mass on the periodic table, we will round that number and talk about it as the mass number, okay? So we would refer to this particular neon atom as neon 20 because its mass is very close to 20. The reason why that's useful is because if you know the number of protons and you know that a proton and a neutron all weigh basically 1 in this scale, then you can actually determine the number of neutrons. So if the mass is close to 20 and we know it has 10 protons, then that implies that it's got about 10 neutrons as well. So an easier way to think of it is just round this to the closest whole number, so 20 in that instance. And then you know that neon has 10 because all neon has 10 protons. It's not neon if it doesn't have 10 protons. And so that mass number is equivalent, see, I do have this written down, so let me highlight it, to protons plus neutrons. Okay, so if your protons is 10 and you know the total is 20, then obviously the neutrons needs to be 10 as well. So there's a slight difference between mass number and the actual atomic mass. The mass number is just rounded. The atomic mass is going to be close to that, but just like a little bit off. For a couple of different reasons. We'll get into that on Wednesday. Okay, we'll probably come back to this one on the next slide a little bit more, because this is typically used for isotopes where we have varying numbers of neutrons. So we might have like neon 20, we also might have neon 21. So that would just be differing by 1 neutron. Okay, so we'll come back to this symbol. This is one, so this one you're gonna see on the periodic table a bunch. This is one that you'll use to write down chemical symbols if you were handwriting them, okay? So you write the symbol in the middle. You write the atomic number, which is equivalent to the number of protons. I'm going to show it to you on the periodic table in a second as well. And then you write the mass number up here. So protons plus neutrons. Okay, so protons down here, protons plus neutrons up there. And it's a little bit repetitive to say the 10 and say neon, because like 10 and Ne are always tied to each other, just like carbon and 6 are always tied to each other, because if something has 6 protons, it's carbon. If it's carbon, it has 6 protons. Okay, let's go down to the periodic table for a second. So So if you want to pull up in a separate one, that's fine. Or if you just scroll down a few slides, I've got a whole slide that's just the periodic table. So in red, you guys can see those are the atomic numbers or the number of protons. And then they have those atomic masses listed on the bottom. The symbols we're going to write, though, are like a rounded off version of that. Okay? Okay. I think I have this coming up, and maybe I'll just say it now. Yes, right there. So element name is often omitted. So I already did that. I crossed it off. So what you need to do, because your periodic table and really most periodic tables don't have the names listed on there, is you need to be able to know if I say neon that you know to go look for Ne, okay? Or if I say lead, you need to go look for Pb. So some of them are easy, like neon, Ne, or carbon is C, but like lead comes from the Latin plumbus, so that's why it's Pb. Okay, so some of them are a little bit trickier. So the ones that you'll have to have memorized are 1 through 36, silver, gold, mercury, and lead. So let me go over to the periodic table and just kind of highlight those again. You do not have to memorize any of the numbers. You will have this on every exam, a blank copy. So you don't have to memorize any numbers because they're literally all right there. What you need to know is how to tie the symbol to the correct element. Okay, so 1 through 36. Silver, gold, mercury, and lead. So all of those, you should know name and symbol interchangeably. So I'm sure there's like, you could probably even go on, what is that, Quizlet? Is that what it's called? You could probably go on Quizlet and like type in like Christiansen chemistry symbols, and there probably would be one saved in there already that has these specific ones. I didn't make it. I'm just saying someone else might have made one and titled it correctly. But you just do, quick flashcard kind of thing. Make sure when it comes up with iron, you know to say Fe. If it comes up with S, you know to say sulfur, and so forth, okay? No numbers involved. Be aware that in the symbols, the first letter is always capitalized, and the second is lowercase. So CO with a small o, that's cobalt. CO with a big O, that's the molecule carbon bonded to oxygen. Okay, that's two different elements. So the only time you're writing a small letter, a lowercase letter, is if it's part of a given element. Every other time you need to write them big so that you're indicating they're separate atoms. And then, I think we've talked about this already, but like if you have subscripts, that means you have multiple of those atoms. So CO2 would be 1 carbon atom and 2 oxygen atoms. Okay? If you wrote like Fe2O3, that would mean you have 2 iron atoms. Fe is the iron atom, so 2 of those and 3 oxygen atoms. Okay? All right. So back to the symbols. We're going to do some practice with these just so you get comfortable, being able to interchange between atomic number and protons, between mass number, protons, neutrons, and kind of mix things together. The only one that we haven't talked about since last class is the charge. So just be aware if there is a charge, we'll write that up here in the symbol. So right now there's nothing written there, meaning we know that we also have 10 electrons. If I were to write a symbol up there, positive or negative, that would indicate either a loss or gain of electrons. So the other examples we're going to do are going to have those. Oh, do I want to do that yet? No, we're going to talk about this first. So we'll do these practice next. So this is what I mean by we're going to practice these symbols. You can see in this example, that one has a charge listed there, 3 minus, meaning it has 3 extra electrons. Okay, so we'll come back to that in a minute. So just like formally talking about isotopes so that you have it in your notes and you're clear on the differences. So an isotope is where you have the same the same element, and you have a differing number of neutrons in the atom. Okay, so the most common form of neon, 90% of the neon found everywhere. Yeah, we can't go measure all of the neon, but we do have ways of estimating like how much of a particular isotope is in different things. Like even in the stars, we can get ideas of that based on lots of cool stuff that we're not going to talk about yet. Okay, so most neon is 10 protons, 10 neutrons, so its mass number is 20. A small fraction of it is 12 neutrons, so neon 22. 10 protons plus 12 neutrons, neon 22. And then a teeny tiny little amount is 10 protons, 11 neutrons, or neon 21. Okay, the most common example of isotopes that you've probably heard of is carbon-14 dating. Does this sound a little familiar maybe? So carbon-12 is what most carbon is. It's even more dramatic of a percentage. I think it's like 98 or 99% of carbon is carbon-12. There's also a little bit of carbon-13, so 7 protons. And then a little bit of carbon-14, which would be 8 protons. So when you get a higher number of higher number of neutrons to protons, that increased mass can tend to make the nucleus a little bit unstable. So there is a force that holds all of these protons and neutrons together, and the more you try to shove in there, the more difficult it is to be held together. And so sometimes those nuclei will actually break apart, okay? That's what we would consider nuclear chemistry or a nuclear reaction. Nuclear, like nuclear energy, nuclear weapons, that's what they all rely on. So you've probably heard of like using uranium or plutonium. Those are really heavy elements. So uranium's down here. It's actually the heaviest naturally occurring element. Plutonium is, where is it? I thought it was P-O. It's not this one. There. Or is that polonium? Okay, I guess I don't know for sure. I'm going to have to look it up because I think this is polonium. This is probably plutonium, but it's not naturally occurring. Okay, so uranium, if you've ever heard them talk about like nuclear energy or talk about heavy uranium versus light uranium, so the heavier isotopes of uranium, the ones that have more neutrons, are again more unstable, and so they have the tendency to break apart. And when they break apart, they release a lot of energy. So that's what energy is being harnessed when we're talking about nuclear reactions, is the energy of when those break apart. Now, nuclear weapons are a little bit different. They're actually a lot of the times combining things, like when we talk about hydrogen atoms. Okay, so what does this have to do with carbon-14? Because that was the example I was going on. So we get these unstable nuclei that tend to break apart. Carbon-14 breaks apart very predictably. Like there aren't a lot of things that affect it or speed it up. So when you're a living organism, a person, a plant, whatever, you're constantly, all of the carbon in your body is constantly being cycled through. So like you're eating or you're manufacturing sugars from the sun if you're a plant, and your carbon is constantly getting turned over. So all of the carbon atoms in your body are being cycled through. So you have a relatively stable amount of carbon-12, carbon-13, and carbon-14 that's reflective of what's in the earth and therefore like what you're eating. Once you die though, or let's say it's a plant. So once the plant gets cut down, the tree, and it's no longer making its own sugars, that carbon then starts to decay and it's not getting regenerated. So that carbon, the carbon-14 doesn't get replaced. So let's say there's like a certain percentage of carbon-14 to start, that starts decaying at a very predictable rate. So if we go in later and measure the amount of carbon-14 in a tree, let's say, then we can backtrack that to know how much carbon-14 there was originally based on a particular amount of time. Okay, so we like know how much it should have had percentage-wise at the beginning. We know how much it has now, and that can tell us, you know, how long it's been dead for, basically. How long this log has been sitting there. Okay? All right, so that's a kind of cool use of isotopes. So now let's go ahead and do some example problems. I'm going to do the second row with you, and then I'll let you guys work the other ones on your own or with your neighbors. So protons, neutrons, and electrons. And we're going to write the symbol. And then sometimes it's either going to give us the charge or we're going to have to write the charge in there. Okay? So you will need a periodic table for this unless you're a nerd and I don't even have all of the proton atomic numbers memorized. So, okay, so 17, I'm going to look for what has the atomic number 17 because protons is atomic number. Okay, so I'm going to go to my periodic table. I'm going to look for 17, and it's chlorine, Cl. So I'm going to go put that symbol here, Cl, and the 17 goes down here on the bottom. Like I said, that's kind of repetitive to put both the number and the symbol, but it's fine. And then the mass number is going to be protons plus neutrons. So they tell us the neutrons here. So the mass number on this one's going to be 37. You don't want to get that from the periodic table because they are talking about a particular isotope here. The periodic table is actually an average mass of all the isotopes. We'll talk about that on Wednesday and do some calculations surrounding that. And then the number of electrons, normally we would just say, oh, it's the same as the number of protons, right? It's 17. But they're telling us that this actually has a charge of -1. So that must mean that there's 18 electrons or one more than the number of protons. And the way that we show this on the symbol is to just put the charge up at the upper right there. When it's 1, we don't write the 1. We just write positive or negative. And if there is, 2 or 3, you write the number first and then the charge. So it's 3 minus, not -3. Now, if you're saying the charge, it's not wrong to say -1 if you're saying it. In the symbol, it's important to write it number first and then charge because it can get confused with if you mess up how you're writing it, it can look like, was it 3 atoms or was it, -3 charge? Okay, so go ahead and fill in the rest of this chart. And I'll give you guys a minute or so to work on it by yourselves. Then I'll start to fill it in so you can check answers as you go. And chat with your neighbors as needed. Did everybody fill out the roll? Does anybody else need to? Okay. Okay, so I'll go ahead and fill these in just for you to check as you're finishing up. Nope, that's not a 3. Yeah, see, I hate scrolling like that to find things. I would much rather have like a separate tab open. So, exam equation sheet, that's why it's good to always have that handy. I'm like second guessing myself. Did I look that up right? 40, yes, was ER. 34 was SE. Okay. All right, so as you're finishing up, go ahead and check your answers. Yeah. So if you are given the mass number, like on the first one, then these two should add up to this. So you just take 75 minus 33 in that instance. If you're given the number of neutrons, then you add them together to get the mass number. So you can kind of think of it like an equation. The mass number equals protons plus neutrons. I guess you could do the same thing for charge if you're like getting mixed up. Just remember that electrons are negatively charged, so it's going to be like charge would be protons minus electrons. So then if you have extra electrons, like in the chlorine one, you have 17 minus 18. That's where the -1 comes from, versus the zirconium, let's say, which would be 40 minus 38. So that's why it's a +2. Just a good reminder, I guess, of keeping electrons negative. Okay, let's just do these other two. You probably don't need extra practice, but, you know, it's never a bad thing, and I think we have time for it. So just a couple more practice problems. Okay. All right, any questions on the symbol stuff? Make sure you get started on memorizing symbols to names for those ones that you're required to. It'll become pretty familiar. There'll be plenty that you'll have memorized that you didn't even like intend to. Yep. Okay, so the rest of the class we get to talk about the periodic table, which is just so fun because it's like the one history story we just can't skip over. So I do love the history stuff, but we don't generally have time for all of it. But this one's like, we've got to do it. So it is a great story, so much that like when a chemist, or I would say most any scientist, looks at the periodic table and has like an understanding, not just of like, oh, look at all these elements and it's so nicely organized, but like all of the information that's kind of embedded in the shape even of the periodic table is what's very, beautiful to a scientist. So much so that like we have a framed periodic, my husband's a chemical engineer, so he gets it too. But like we have a framed periodic table like as artwork in our house. So, all right. Okay, so the modern periodic table, the one that we're used to seeing, is surprisingly not that different from what it was when we very first started, when Mendeleev very first started developing the periodic table. So he did not know anything about subatomic particles. He did not know about protons and electrons. And he did not know, there's something else. It's like an important piece of information there that he didn't know. I mean, I guess as a part of that, he certainly didn't know anything about mass number. Atomic number. It's going to come to me, the thing I'm missing. But he did not know that there were such a thing as protons and neutrons. So this was after Dalton, who established the idea of atoms themselves, but before subatomic particles like protons, neutrons, and electrons. Okay? So this basic shape was what he developed and the order that the elements went in. But at that point, there were, I don't know the exact number. Does it say on here? No, it doesn't. I don't know exactly how many elements, or don't remember at least how many elements they were aware of at that point. But there was quite a bit of data out there, but also quite a bit of elements that hadn't yet been discovered. So there's all of these different elements that make up the universe, and it's just a matter of identifying them. So they had quite a bit of those elements identified, and what he did was he took all of that data and said, we need to make sense of this and organize it so that it's in a more usable format. So the best idea he had to start with was ordering things by their mass. So if you just look at mass, so the bottom number here, you can tell that the periodic table is roughly laid out by mass. So like 1, 4, 7-ish, 9, close to 11, 12, 14, 16, and so forth, okay? So they roughly go in mass order. If you start at the top, go through each row, and then go down row by row, okay? So that was the point where he started with. And then he said, obviously we don't just want like a list in order, but we want to tie them together somehow by their properties. So at that point, he said, okay, how are we going to organize this by property? We should somehow group together things that have similar properties. So he orders them by mass, and then he says, a way that I'm going to do this to group them by property is when I see one that has a similar property, that's when I'm going to start a new row. So this is him ordering it by mass. He gets to sodium and says, no, this is not, just his experimentation, lots and lots of data over, lots of years. Sodium has really similar properties to lithium. So I'm going to pair that one down here, and then I'm going to start to identify, the next mass that has a similar property to another one. And he starts organizing them in this way. So interestingly, lithium, sodium, and potassium, if you've never seen this, Google it on YouTube. I'm sure it's readily available to see a reaction of any of these in water. So you put a little bit of lithium in water and it kind of like fizzes around on the top. You put some sodium in water and maybe you get like a little bit of spark. You put potassium in water, you're probably and I know this from experience, gonna get like maybe a little minor explosion or something. So I did this once in, I was like 19. I probably had no idea what I was doing. But I was like a TA in a chemistry class, and it was we had this like lab assistant that they would like bring you little demos to your classroom if you wanted. So I did that, and I guess I just cut off like a little bit too big of a chunk, and it like flicked out of the bowl and like hit someone's textbook and like burned a small hole in their textbook, and then landed on the carpet and burned a bigger hole, and it was a little bit smoky. And I never fessed it up until like my senior year of college, and the professor I was teaching for, I said something about it, and he's like, "Oh my gosh, that was you? We like got like this email about like what's this hole in the basement of the Benson building? Like what happened there?" It was me. Anyway, the further you go down the periodic table, the more dramatic that is. So if you were go even further to like rubidium, you're gonna get like a huge explosion. So I think there's like stuff on there of people doing it in very large containers of water. You just have to Google it on your way to your next class. Okay, so he starts grouping together things that have similar properties, but also going by mass. And thankfully, as he's doing this, he's finding like, okay, I had beryllium, I lined up sodium under here under lithium, and my next mass one actually lines up with one that's right after lithium. And he starts seeing all these trends, like he gets down to chlorine and it's got similar properties to fluorine. So he just keeps the columns lined in what we now call families. So if you scroll down here, we have like names for given groups. So the ones that are explosive in water, sodium, potassium, lithium, those are called the alkali metals. That's that first column. The second column is called alkaline earth metals, easily mixed up. The halogens are these guys over here. You've probably heard the noble gases. Okay, so things in a given column have similar properties and are sometimes given names, and then going across the periodic table, we see that it's in increasing mass. Okay, here's the exciting part of the story. So he's going along and doing this, and I guess I need a periodic table. There we go. So he's going along and doing this, and primarily this is for the main group elements. So this side here and this block over here, we consider those the main group elements because they are the most predictable. The ones in the middle, those are called transition metals. And the ones down here, the lanthanide and actinide series, those have, I would say, more similar properties to the transition metals. So they're a big chunk of metals that have less predictable properties. We'll explain why, probably not till the second semester. Okay? So sorry if you're not taking Chem 2. So these main group elements, he goes through and does this, and he gets to certain ones and leaves a blank. So I thought it was germanium, but apparently it was silicon as well. Those hadn't been discovered yet. Like, he didn't know about silicon or germanium. So he gets to aluminum, he lines it up with boron, and then the next mass that he has is phosphorus. So like the inclination would be, well, put it in order, but he's like, it doesn't line up with carbon, it lines up with nitrogen as far as its properties. So he leaves a blank on the periodic table and is like, I think there's probably something there and we just haven't found it yet. And he does this with multiple atoms, which is just phenomenal. The other one that's interesting is like tellurium and iodine. If you notice, their masses are swapped. So iodine has a mass of 126 and this is 120, almost, I guess that's more like 128 and 127. Anyway, they have flipped masses. There aren't very many examples of that, but so he started with putting tin, antimony, iodine, tellurium, and then he was like, that doesn't make any sense though, because iodine follows bromine and tellurium follows selenium's properties, so he flipped them. Okay, so he does all of this before he even knows about protons. Okay, no knowledge of protons at this point. So then you look through the periodic table that he laid out before we knew that these had these given number of protons, and it lines up perfectly. Is anyone else getting chills? Right? It lines up perfectly. He leaves a hole for 14, right? It's like 13, blank, 15, 51, he knew to flip these and put this one first instead of that one, even though its mass wasn't off, was off. So cool. All right, I'll stop. Okay, so that was Mendeleev. Now just kind of some key points that we get, like basic information from the periodic table. Metals versus non-metals. This is always kind of shocking to people if they haven't seen this before. The tan colored ones are metals. So the vast majority of the elements that make up the universe are metals. It's a little bit surprising, I feel like. Metals have, the properties are listed on the next page, but they're what you would expect. They're really good at conducting heat. They're good at conducting electricity. They're malleable, meaning that we can bend them and shape them. If we start to melt them a little bit, we can soften them and put them in a shape that we want. Whereas non-metals, in their solid form, are generally really brittle. So think of a chunk of charcoal that's pure carbon. So it's, breaks really easily. It certainly doesn't conduct heat or electricity. It's going to burn up before it conducts any heat. Okay. And there aren't very many of them, but they are also the ones that are the key components of living things. So I would say these three plus hydrogen are, I'm just making up a number here, but 95% of what living organisms are made of: carbon, nitrogen, oxygen, and hydrogen. And then we've got a little bit of phosphorus and sulfur in there, and then kind of more micro levels of other stuff. Okay. The purple ones are considered metalloids, and they basically just have properties that kind of fall in between the two. So they're not clearly a metal or a non-metal. That's pretty amazing too, that all of this stuff is embedded in that original shape of the periodic table. Okay, so I said those verbally, those are the properties. And we talked about main group elements that have very predictable things that happen to them, how they react, and the transition elements are much less predictable. I'm going to talk about charge as our last thing, and that'll kind of explain some of this. We talked about families already. Okay, so the last thing we'll talk about today is charge. And this one also very consistent with the shape of the periodic table, the original shape of the periodic table. When elements form ionic compounds, so an ionic compound is a positive ion like sodium, and it loses an electron to become a positively charged ion. A nonmetal like chlorine gains an electron to become negatively charged, and then they stick together because they're positive and negative. So that's sodium chloride, table salt, very basic, fundamental example of an ionic compound. So when we look at elements on the periodic table, when they do form ionic compounds, the main group elements form ions in a very predictable way. Okay? So in the first column, all of these guys tend to lose one electron. So when they form an ionic compound, they will all have a +1 ion. So we're going to get to naming in the next couple weeks. And you're going to be like, how do you know that potassium's a +1? Because it's in column 1. Okay, this is the first time I'm going to tell you. I'm going to tell you 3 more times. In the second column, those tend to lose 2 electrons, so they become +2. The transition metals, one of the reasons, not why, but one of the things that is very unpredictable about them is that we cannot predict their charge very well, and they can form multiple charges. So chromium, for example, we see it as a +6 and a +3. So it has 2 different charges that it can form. It might lose 6 electrons or it might lose 3. Thinking of gold, I want to say is no, that was iron. Iron's +3 or +2. There's no real rhyme or reason to why it is one or the other. It just kind of depends on the individual circumstances. When we get back to the main group elements, these ones, even though they're not labeled, these ones are pretty predictably +3s. These guys don't tend to form ionic compounds. That's why there's nothing written there. Then we start to gain electrons on this side with the nonmetals. So these guys gain 3 electrons. to become a -3. These ones gain 2 electrons to become a -2. And these gain 1 to become a -1. So very like ordered, structured things that we can pick off of the periodic table. So when you sit down to an exam, you are going to have this exact periodic table, blank obviously, and you can use it to your advantage whenever there's anything that you have to memorize, like let's pretend it's the charge on ions. You know, you get your table, you're allowed to tear it off and start jotting down stuff. Like you jot down, oh, this column is +1, that column is +2, +3, -3, -2, -1. It's a really good place to kind of summarize some of that information for yourself and also give like a visual context for how you do your memorization. Okay? All right. Have a good day, and I'll see you guys on Wednesday.
Neutrons affect the density of an element, like in real life?
Yes, because it would be heavier if there are more neutrons, and the size doesn't change significantly.
So like, as in like carbon-14 would be a diamond? Is that
No,
accurate to say?
no,
Oh, okay.
yeah. So it doesn't affect how it bonds, because that's what diamond is about. How it bonds. Like, is it going to be charcoal or is it going to be diamond?
Right.
It would affect the atom's density, but the overall density of the compound is more likely how all of the atoms come together.
Okay.
So, yeah, it's good clarification.
And then, oh yeah, are some elements more likely to be unstable isotopes, like in the, like, is
Yeah.
that more likely than them being stable?
Yes, the bigger they are, the less stable they are.
Okay.
And iron is kind of the cutoff point. So everything above iron, we tend to see that it has a lot less stability than the smaller ones.
Okay.
But anything like carbon-14 is less stable than carbon-12, the bigger it is. Yep.
Okay, gotcha. Thank you.
Yep. Hi.
I actually did figure out the.
Yeah, you emailed me about it, right?
Yeah, I'm sorry about that.
No, you did email
I
me.
thought it was Sunday. I was convinced.
Oh,
I even called my
yeah.
mom. I was like, "Damn, I'm not gonna be able to do it."
Yeah.
And it was Saturday, but I think I'm gonna sign up for tutoring for
Okay. You mean other way around. You thought it was Saturday and it was Sunday.
No, I thought it was. I thought it was Sunday and it was Saturday, so I thought it was due that night. It was
Yes.
due to the next night.
Okay, yeah.
But I'm having a lot of trouble with the conversion, so I
Okay.
have to do tutoring. Do
Yeah.
you think, like, when
There's
I
not like a particular person if you just go to the tutoring center, like, because there's so much, I don't know if this is the question you were gonna ask,
Mhm.
but there's so much, like, we all use the same textbook, and
Okay.
I end up teaching like, 75% of the classes, if not more. So like a tutor that's doing it, that took it 2 years ago, is still probably gonna have had me.
Okay.
So there'll be some consistency there, but.
Do you think I need any example problems in this class, or will they already have it?
No, they'll probably have stuff.
Okay.
You could take yours and you could take like your homework,
Okay.
but they could easily find something if you just kind of isolate, like, this is the kind of thing. I say that, but now I'm like, no, it's probably a good idea to just bring like your class notes.
Okay.
Or your homework ones. I don't think I've posted a practice exam yet, but I'll do that before the end of this week too.
Okay, thank you.
Yep. Hi.
Okay, I noticed I still wasn't on the
Ah.
sheet.
Okay, what's your name? Okay, let me pull it up in Banner then and make sure. Last name?
West.
I feel like I've seen your name on there though. And it's on your schedule and stuff,
Mhm.
right? Okay.
Yeah, I don't
It's-
think it was on there last class.
Yeah,
Either.
okay. I am going to check, but if you don't need to be anywhere right this second, then just hang out so that if there is an issue, we can resolve it. But I kind of think it's just me. Did you add later than, like, I don't know, were you here at the beginning of the semester, or did you add like
Yeah,
later in the week?
here.
Okay. I don't have a good explanation then.
I don't think I probably didn't put my name on it the first few days.
No, that's not where I grab it from anyway, so that shouldn't be it.
Cause like I'm in the Pearson stuff.
Yeah, and it's showing up in your Blackboard. It's fine then. It's just me. I'll just make sure to change it on mine But I'll verify it, but if you're showing up in Blackboard, then you couldn't be unless you were registered, so.
Okay.
Okay, yep, thanks for letting me know.